All right, everyone. So hopefully you're enjoying the conference. This technical stage is going to have a fantastic set of topics. And in this first session, we're going to hear about the life of a transaction throughout the Hedera network. So it's going to be a fantastic overview of that journey of a transaction. So I want to welcome back to the stage Richard Baer and also Jasper Pott to take us on this journey. Welcome.
See if my guy goes. Okay, great. Back up. All right, so we're going to talk about the journey of a transaction through the network. This was originally I don't remember how many hours it was supposed to be initially.
It was supposed to be 3 hours, ended up being 6.
Yeah, so we could spend a lot of time on this, but we're actually going to have to try to fit this into 30 minutes. So we're going to do our best, give kind of an overview. Our hope is that by the time you get to the end of this session, at least you'll know what the main building blocks are of the network and kind of how it fits together. Oh, and Jasper, you should introduce yourself.
Yeah, so everybody, I'm Jasper Potts. I'm a distinguished engineer and architect for Hedera at Hashgraph, and involved in pretty much everything.
Yes, pretty much everything. So we're going to go on a journey here, and we're going to take a transaction from kind of where it starts to where it ends along the way. But before we do that, we got to lay out a little bit of understanding of the lay of the land. What are the different components that we're going to be talking about, and kind of what are their responsibilities, how do they fit in, and then we'll be able to walk that transaction through this entire story. So one of the first thing that we have on here is a relay node. I don't know, you heard about the JSON-RPC relay in the last session, and you may have been wondering what the heck is that thing. A relay node is a totally permissionless node. Anybody can run a relay. In fact, there's many companies out there that run supported relays, and it is in production. And what it does is it provides the Ethereum compatibility. The relay node implements the Ethereum JSON-RPC APIs, so that if you use MetaMask or you use Forge or you use Hardhat or whatever Ethereum tool.
Any Ethereum tooling just works out of the box as if it thinks it's another Ethereum network. Just has a network ID, looks like Ethereum network.
You can ask it for blocks. It'll give you back blocks that it can understand, all those sorts of things. So,
and behind the scenes, it talks to all the other nodes.
Right. Consensus node is the thing that actually takes your transaction in. It maintains the live state. It brings your transaction to consensus. It executes that transaction, modifies the state, and then it creates and exports the blocks. The block node is permissionless. It's not yet in production, but its responsibility is to store and serve blocks. So in this story, I'm going to talk about block nodes as if it were in production. Today, it's still this record stream that's coming out of it, but this is really sort of an essential piece of what we're building. So its job is to store and serve the blocks. And then the last piece is a mirror node, which when I first came, I thought mirror node is a strange name for this thing. What the heck is a mirror node? It's essentially a query engine that you can use. You query its REST APIs or its other APIs in order to find data that's in blocks. So that's the role of the mirror node. So with that in mind, this is going to be our journey for today. We're going to talk about 2 different starting points for a transaction. You can have a transaction goes through relay or that goes through this other path. And then we'll talk about consensus and execution. We'll talk about the block nodes, what happens with blocks. We'll talk about being able to index and query those things, and then how to explore all the data when we get to an end. So our transactions are going to pass through this entire journey. So let's go ahead and start with the very beginning, which is you need to create a transaction. There are many different wallets that are supported on Hedera, including some Hedera native wallets like Blade and Hashpack, and even Ethereum wallets like MetaMask. I've even used the Brave wallet. Anything really that works on Ethereum will also work on Hedera. And when you have, this is just a simple example. Let's say our transaction we're going to talk about today is just a simple crypto transfer. I'm just transferring some HBAR from one account to another, or I'm transferring an NFT from one account to another. So in this case, I might initiate it in my wallet, or I might initiate it in an app that then opens up my wallet to sign the transaction. But in either case, there's a wallet that kind of sits at the very beginning of this journey.
And depending on whether it's an Ethereum-compatible wallet or a native one, will be which one of those 2 paths it takes.
Exactly. So if we're using the Hedera native APIs with a Hedera native wallet, we're going to, you create your transaction using your app or using one of the wallets themselves or any of our SDKs. And I have a list of the different languages that we support, that we have SDKs for. And then what they'll do is they'll take that transaction. Our system uses protobuf as the binary format for all of the communication. So it'll take that, turn it into some byte array, and then the wallet's going to sign it. And then what your app will do, if your app is the one that created this transaction, or the wallet, if you're doing a transfer inside the wallet, is it's going to select one or more of the consensus nodes, and it's going to submit that signed transaction to the consensus nodes. So here we have our little transaction. It's been signed, and it's going to get sent to a consensus node. Now, if it was an Ethereum, you'll follow this flow, which is we're going to implement this. The relay implements the Ethereum JSON-RPC APIs. So in this case, you just create a transaction like normal, send it to the wallet like normal, gets signed like normal, gets sent to a relay node, and then the relay node is the thing that's going to send it.
And the key part here was just, we wanted everything to just work. It should be seamless to the app, whether it's talking to Ethereum or talking to Hedera. It can talk directly to the relay. It will then take that transaction that's signed as Ethereum transaction, wrap it in a Hedera transaction, forward it to one of the nodes, do all of that for you, and just make the experience seamless, really.
Exactly.
Yeah. You shouldn't have to know it exists.
So the transactions are created by your application in Ethereum. They get signed, goes to a relay node, and then that transaction just goes directly to consensus node. Consensus node will unwrap it and say, oh, I see here that you're doing an HBAR transfer, and it'll do that work. Or it says, oh, I see here that you're calling a smart contract. OK, we'll call the smart contract.
And that was one of the important hips Richard mentioned 20 minutes ago, the change about who pays in this process and streamlining that process, and that's something we're working on to make it work even more seamlessly, really. Anywhere there's friction in this process, we're working really hard to remove that friction.
Yeah, our goal is for this to be completely compatible so that you can just lift and shift an application, run it on Hedera, and benefit from all of the performance, the fair ordering, and the other benefits we provide. Okay, so that kind of got us through the first few steps of our journey, whether we came through the traditional SDK approach, if you will, or if you're coming from the Ethereum approach going through the relay. So now we're going to talk about this part. Now, our nodes are a combination of two pieces, consensus and execution. So when we talk about a consensus node, it does both of these tasks. It's responsible for both of these tasks. And we're going to talk a little bit about both of those tasks and what they look like. So I have here just a simple diagram of kind of what a 32 or I guess 33 node network would look like. These nodes, each one of these consensus nodes, they work together. The thing that I feel is the most critical and important part of the whole system, that what really matters are these first 2 points. Hedera is unique in that this is a completely leaderless and democratic system. Bitcoin is not like that. Ethereum's not like that. They are leader-based, which is why you can front run, right? Because whoever's creating the block gets to select what transactions go in that block. Everybody else just validates that was a valid block, but there was a leader that...
And they move the leader around rapidly. Every block is created by a different leader, but there's always a leader.
And they pick a leader retroactively. They didn't know who it was ahead of time. Maybe they pick it, in retrospect. It's a very clever system, but it's different than ours. Our system is leaderless and democratic. Every single node is going to deterministically, independently, sort the transactions in exactly the same way. That is what the Hashgraph algorithm does. So they all work together and agree on the order of the transactions. They all independently execute those transactions, and then they all share the root hash of the state tree with each other to verify that they all came to the same result in the end.
And the consensus part is super simple in concept. It's take a bunch of transactions, fairly order them, send them to be executed. There's nothing more complicated than that. The challenge is all how to do that entirely fairly, even if any one of the nodes is a bad actor, and without anybody being able to corrupt it, and entirely safely and securely. That's where all the hard work
At a
is,
super high
all the
performance.
genius, and that high performance and low latency.
Yeah.
You know, the big thing of Hashgraph that changed, you know, the computer industry forever have been trying to work out how can you have Byzantine fault tolerant and low latency, and it pretty much concluded that the two were mutually exclusive. And Hashgraph solved that problem. It allows us to have low latency and Byzantine fault tolerance.
Yeah, in fact, when Lehman was working on Hashgraph, he would work on it for a bit, and then he would say, this is impossible, can't be done. These things are mutually exclusive. You cannot have low latency and ABFT. Can't do it. And then it would sort of bother him, and he'd come back to it, you know, a few months later and be like, I don't know. It seems like maybe we should try again. And then one day he got it. And this is the part that, to me, is so fundamental. And everything else that we talk about is based on this idea that these nodes are independent actors who independently order the transactions in exactly the same way, execute the transactions in exactly the same way, come to the exact same state at the end, and then they produce identical blockchains. So unlike a normal blockchain where you've got forks, and you have to prune some of those off, you get the uncles or whatever, and you got to prune them off, the blockchain produced by Hedera is linear and never, ever forks.
And as soon as you've got a block, that block is final and has complete proof, complete trust, and everything to do it.
Yeah, final forever. You have guaranteed finality. And I guess we should, when we talk about low latency and high performance or high throughput, it's currently on mainnet. I saw this morning, it was actually a good number. It was 2.5 seconds for finality. So 2.5 seconds from when the transaction shows up, it has been ordered and executed. And typically we see it around 3.5 seconds. It's kind of the typical thing that we have in the
You kind of wish that conventional banking was like that. You go and buy a house, you wish 2.5 seconds later you could own it. But
yes.
no, not quite there yet.
It would be nice. So this is a very simplified view of what the consensus node looks like on the internals. And I've split it into two parts. We've got our execution part, and we have our consensus part. And what happens is that when your app sends in a transaction, it uses this gRPC service. gRPC is a Google RPC service that was open
based
source.
on protobufs.
Yeah, based on protobufs. Open
It's like
source
binary REST with protobuf, which gives us lower latency,
low bandwidth.
Low bandwidth. We can get a lot more queries within the same amount of bandwidth.
Yeah, and highly used in the industry. This guy, when he receives a transaction, one of the things he does is he checks to see, are we too busy? One of the things you have to, of course, defend against are denial of service attacks, people who just sort of try to overwhelm your nodes. So there's a throttle that happens up front where it looks at your transaction and says, okay, do I have capacity to handle this? If he does, he'll then send it to this component that's called an event creator that creates, it's essentially the message that's going to get gossiped to everybody else. And that message that we call an event may have many transactions in it. So this guy collects some transactions, sticks them in an event creator, or gives it to the event creator, who creates an event that then gets gossiped to all the other nodes in the network. And when it comes out of gossip, it then goes to the Hashgraph, and the Hashgraph sorts all of these events or messages in a deterministic order. And then it produces a list of transactions in a deterministic order. We handle those transactions, modifying state, whether it's our little crypto transfer here, we're going to end up reading the account for the account that's sending the HBAR, the account that's receiving it, the accounts that are going to collect the fees, do the logic in order to figure out what their amounts are, and modify it and stick it in state. And then it's going to pass the information, the final output of this, to the block producer, who then is responsible for exporting a block that a block node then picks up and holds and goes to the mirror nodes and so forth.
And that block will be signed by all the consensus nodes.
Yeah, that's an essential part. This is like the thing that's so cool about the blocks is that they are signed not by an individual node, they are signed by the network using a BLS algorithm.
And this is for the new blockstream stuff we'll talk about in more detail later, but with the new blockstream, blocks are entirely self-contained and contain the full trust of the supermajority of the network.
Yeah, which is so cool, because this is where the trust is derived from, is from these consensus nodes. They're the thing that proves that this has been done correctly, and then they supply these blocks, and then from there you can do all kinds of cool stuff. Okay, so this gets us through our consensus and execution parts. And now we're going to talk about our block node. So our transaction, again, to review, our transaction was created, it was signed by some wallet or SDK, submitted to a consensus node. It went through gossip with all the other consensus nodes. They all ran their Hashgraph algorithm independently, and they sorted those transactions. They handled those transactions. They put the transactions and their results into a block. They all worked together to sign that block. Now they've exported the block. So this blockchain that we have created is the product of the consensus nodes.
And every block refers to the previous block forming the chain. At the point where we switch over from record streams today to blocks, there will be a continuous unbroken blockchain between the two. But we're trying to open up a lot of new interesting opportunities with this. Today, record streams are signed independently, so you have to take the record file plus a collection of signatures from the nodes and do the comparison yourself to know there's a supermajority. That all gets built in now. So you'll just be able to take a block, you'll be able to trust everything in that block, and that block will actually include trust for every block that's previously been produced on the network, the current state of the network, every previous state. It's kind of crazy how much you can prove with one block. I'm really hoping there's some cool ideas that come out of that. And then, the other aim is to try and keep this as low latency as possible. That we get that block to you as soon as possible. Because the thing that's most frustrating is you go and do a transfer from your account to another account. You have to wait.
Sweat bullets.
Yes. You're sweating while you're waiting for that to show up on your wallet to say, hey, that transfer has happened. Our aim is to try and get that down as low as possible. Well into the seconds, and hopefully very few of those. And one day we'd like to be even less.
Yeah, I'd like to compress it down to like the minimum that speed of light allows us to do.
Yeah,
there's some
the
fundamental limits, but pretty small.
The dream is if you get it under a quarter of a second, then nobody notices.
Yeah.
If you get it to the point where the latency is low enough that nobody cares or notices, then when
you win. Yeah, that's it. So in the blocks, our blocks are similar. We call it a blockchain because it fits, right? It's a chain of blocks. But the format of each one of these blocks is unique to Hedera. It's not the same as what you'll find on other networks, although there are a lot of similarities.
Yeah. And if you're accessing it through the relay node, they'll actually take our blocks and convert them to Ethereum-compatible blocks. So there is that conversion for you if you want to access them and look like Ethereum.
Yep.
But there's a lot more interesting stuff in our blocks. So we're trying to solve everything you can get from an Ethereum block, plus loads of cool other ideas.
So we talked about block nodes are responsible to store blocks and to make them, retrievable, right?
Yeah.
You can sort of store and retrieve.
So our hope initially is that block nodes will be able to store the entire history of the network. And we're hoping to plan out for 5 or 10 years. Obviously it depends on adoption. I think at full adoption rate, we could generate a petabyte a month of blocks. So if you're running at full 10K TPS with the biggest transactions we can generate a huge amount of data. But depending on our usage level, hopefully block nodes will store everything. So you'll be able to go and get any block from them. You'll be able to get that both through a live streaming API where you can stream the current live blocks, or through historical blocks. You can stream historical blocks. So this will give a really nice access to that data, both random access and streaming access to it, plus be able to do value-add services on top of that, like be able to take any piece of data in that and generate a proof for you. And I think there's lots and lots of use cases that can be generated on those proofs. Interledger communication is one we talked about earlier, but as Rich said earlier as well, that we've had lots and lots of problems come up, and we always say that block nodes are the answer, because once we can create easy, cheap proofs to prove anything the network has done, that opens all kinds of doors. And to try and make those proofs as concise as possible. And you could also use zero knowledge to compress them even further if you wanted to.
Yep. Yeah, and I think sort of the fundamental thing to think about with respect to these block nodes is they're totally permissionless. Anybody can run one. And it works because you don't have to trust the block node. All the proof is in the block because the block was produced by the consensus nodes and they signed the block. So if you got that block on a clay tablet 100 years from now, 1,000 years from now, you could turn it into bytes, you could verify the signature, and you would know that block was absolutely produced by the consensus nodes. There's no doubt about it. It doesn't matter how that thing was given to you. If you have a block, you can independently verify everything that's in it, a state proof out of it, a proof that some message or memo or something was in that block, proof that a transaction was in the block, all sorts of things you can prove just from having the block.
And that was really an important design criteria, was to carry that trust with the block. And so anybody who gets one of those blocks has the full trust in the network that the data in there is trustworthy. And so you can pass that around. It can go through as many different block nodes as you like. It can go any kind of complicated network, and you can verify all the way back to the consensus network that everything is trusted in there. You don't have to trust every party that passed it to you.
So I drew this in kind of it might be kind of weird. You're looking at this and you're saying, so there's a whole lot of these little block nodes out here. What is this tree or graph supposed to represent? So the way that this is going to work is that each consensus node will pick one or more block nodes that it wants to send its blocks to. So if I'm running a consensus node, like if I'm the LG node or something, I might have like an LG block node that I'm going to send my blocks to, or I might have several block nodes so that I can always send my blocks somewhere to make sure that they're safe. Those block nodes can be queried directly, or another block node can receive those blocks from one of those primary block nodes through Gossip or through streaming. If you do it through streaming, you get super low latency. If you do it through Gossip, you get it for free. So there's two different methods that you can use in order to try to get that information.
And streaming's going to be there from day one, and Gossip's coming later. But the other one interesting use case of that is you could run a block node inside your own firewall. So you can run a block node inside your firewall, pulling in data, and then all of your internal infrastructure and stuff can run off that one block node. So you're only paying for the bandwidth and access to that data once, and then you could have thousands of internal servers accessing that data with super low latency.
Or if you wanted to build your own block node that maybe had some additional value on it, maybe it had some abilities to look inside the blocks and collect statistics, or you were going to go to this block node in order to produce your state proofs or whatnot. You could have you could run your own independent block node. You could have your own economy around it. You could have people who pay you monthly for it or pay you a
and you can build all kinds of value-added services on that. They can scale horizontally.
Yep.
There's all kinds of cool things. And the consensus node's responsibility is to pick a block node that it trusts will store its records forever, and ideally pick one that has low latency.
Yep.
It has two criteria. It's got to trust that this is an honorable store of its data forever, because that's its responsibility. Its responsibility as a consensus node is to produce blocks in a fair way, and then to have them stored forever for the access to the network. And so it has to trust the block nodes to do that.
So I have some examples on here where like block node is stream pushing it to this block node, or this block node is pulling it from that block node, or these two where there wasn't an arrow pointer at all, they're maybe just part of some gossip tree where they're gossiping with each other. There's a lot of different models that are available.
Yeah.
Oh yes, a question. So the block node is currently under development.
Yeah, in the Blockstream block node, so block streams are already in preview today. So you can already go to the buckets and get block streams and start building stuff and playing with them. The HIP isn't finalized yet, so you can be able to go and comment on it. So we'd love people to go and try it out, and if they've got any ideas that are cool, totally time to do that. Block nodes are under active development. Again, the HIP for that is open. Go and comment on that. If there's something that's stupid or something that's brilliant you'd like differently, we can totally add to that, and we'll go into a lot more detail this afternoon. There's a million more levels to this.
There's a lot, that one was a 2-hour talk. This one was 6, but that one was a 2 as well. So there's a lot of content we can go into there.
And if you've got more questions, come and find me. I'll be around.
Yeah, I'll be around all day. Jasper loves questions. So now we've got it to the blocks. The next thing we're going to do is talk about the mirror node. So my transaction has gone through all that. It's inside of a block right now. And now how do I get access to that? So mirror nodes exist to allow us to search blocks. And here I show that a mirror node could be getting blocks from more block nodes, so it has redundancy. But in the end, it just needs one block. It just needs whatever the next block was in that chain in order to ingest that. And you could think of a mirror node as just like the search engine. It's like the Google for blocks. It takes the blocks, it digests them, sticks them in a database, and then exposes a bunch of APIs.
And it's an incredibly hard job it does. This is a huge data set. I think we're somewhere in the sort of
over 71 billion now.
Yeah, but also 80-something terabytes of data.
Yeah.
So, and the aim of it is to be able to give you query response times fast enough you can drive UIs. Like we all saw hashscan.io, every time you hit a page on there, it's doing multiple queries to the mirror node. So, it's a big data problem, it's got a huge amount of data to index, and needs to give you very fast query responses so you can drive UIs and be responsible.
And mirror nodes are also permissionless in that anybody can run a mirror node. The problem has historically been that they're expensive to run because you have to download all these record files from Amazon or Google, and so it's kind of limited our ability to get a lot of people to run these mirror nodes. But with block nodes, it's a whole different story now.
Yeah, previously with mirror nodes, I think to download the full history was sort of $30,000, $40,000 in bucket access fees, and then it was a few $1,000s a month in pulling in data. So it wasn't insanely expensive, but it was out of the. It really limited
It's not something
the
you're
ability.
just going to do.
Yeah, there's got to be a good business justification for doing it. So really, we want to bring that cost down and open up the market for mirror nodes as well by making it much easier to get data and data at low latency.
Yeah, and both of the block nodes and the mirror nodes are also designed so that they have Helm charts, so you can just deploy them inside of Kubernetes, and everything else takes care of all the plumbing. So they're relatively easy to run, and they're configurable because you can configure the mirror node so it stores like the full history, or you could just configure it so it has a subset of the history, some of the things that you may care about the most.
Yeah, and block nodes are going to support filtered streams as well, which will let you see a subset. So I think there's some cool things there as well. We'll go into more detail later.
Okay, so now that our transaction has made it into our mirror nodes and they're exposed to REST APIs, now we're going to talk about the Explorer. So this is, the project is called Mirror Node Explorer. The hosted version that we host is called HashScan, but there are other, people host this under other names. Arkaya is one of our community members who hosts a mirror node as well. It's the same, Mirror Node Explorer. So it's the same software being, that anybody can host. And it uses all the mirror node APIs like Jasper was saying. It's got a bunch of statistics. You can search all the transaction history. You can view the smart contract details like Ed was showing in the previous discussion. So there's a lot of useful information in this Explorer. It's very handy and easy to use. So, so this is sort of a simplified view, I guess, of those different things put together. Out here on the far left, you have your app. And your app could either send transactions directly to a consensus node, or it could go through a relay node to hit a consensus node. Once it hits a consensus node, they all gossip these transactions. They fairly order them. Each node independently comes to the exact same conclusion on which transactions there are, the order of those transactions, the state that results from those transactions being applied, produces blocks. Those blocks, each one of them is producing their own blocks that are exactly identical to everybody else. They're exporting those to their block nodes where we have this sort of horizontally scalable read system. You can have as many block nodes as the market requires. You can just keep scaling it for more read and also for more redundancy of storage of those blocks so that blockchain history is stored permanently. You could have your app reading from a block node directly, or you could have the blocks as they go to the mirror node and get digested, and then your app could work through those APIs that are available on the mirror node. And then
or any combination of these.
Any combination. There's so many different ways that you could arrange those puzzle pieces. But again, it's like over on the far left, we're creating the transactions. In here, we are taking the transactions, consensus, applying them, and then producing blocks. Here, we're storing and distributing blocks. Up here in the mirror node, we're consuming it, making it easily queryable, and then your application is off on the right and can consume the results of all that work.
So hopefully this gives you a sort of mental picture of the network, and that was really the aim of this talk.
So in terms of call to action, there's a whole bunch of links here to some of the different projects that are on our HashIO organization. So the HashIO's life or world in GitHub is in HashIO Ledger. So if you go there, you'll find all the different projects that we've open sourced under the Linux Foundation. And the playground that Ed mentioned earlier is a great place to kind of start to learn how our SDKs work and kind of get a feel for how that system works together. And that's it.
Thank you.